Since autonomous robots can help to carry out different tasks involved in agricultural production, a considerable amount of research is being done in this regard. For these applications, the localization needs to be known. The use of a combination of cameras and inertial sensors in the so-called Visual Inertial Odometry systems is a locomotion-independent solution that allows robot pose estimation even in GNSS-denied areas. There are many evaluations of visual odometry, visual inertial odometry, and SLAM systems, and there are also agricultural datasets and other works related to localization there, but we did not find any evaluation in this environment. Arable lands present hard challenges for VIO systems given the visual difficulty due to the highly repetitive scene. The main contributions of this paper are in-depth quantitative and qualitative evaluation of the most relevant state-of-the-art VIO systems on arable lands, development of a framework to redo, reuse, and extend the results presented here. For this, we used ROS that allow us to simulate real-time operation and made it easier to compare results, and Docker containers to facilitate installation and to encapsulate dependencies of each system. And finally, correction and validation of the publicly available Rosario Dataset. All the systems we assessed are shown here. They cover different types of cameras, information sources, and estimation techniques. We should say that for ORB-SLAM3, which is a SLAM system rather than a VIO system, we took estimated poses immediately after tracking, namely without final global optimization, in order to make a fair comparison. The evaluation was performed on the Rosario Dataset. We detected some issues with the data while doing the experiments, so we documented and fixed them. As a result, last parts of sequences 1 and 6 were cut out. Furthermore, because of the requirements of stationary initial conditions for Chimera, S-MSCKF, and RBO, we consider trimmed versions of sequences 1 and 5 that fulfill this constraint. We run each system with default parameters and tune them manually following recommendations of their authors. Among others, IMU parameters were adjusted. The experiments were done several times to check the consistency of the results. As an example, in the video, we can see the outputs of the VIO systems in sequence 4. Since we only have positional ground truth, we used ATE metrics. Mean and standard deviations are presented here. Failures of Chimera and RBIO were expected because of their restrictive requirements to initialize. REBO, which is a monocular system, failed to initialize in sequence 1 and 5. It was particularly affected by IMU saturation. With respect to S-MSCKF, even though the author stated that it is needed to be stationary in the beginning, it performed exceptionally well in most of the sequences. ORB-SLAM3 also showed remarkable results. Basalt and Robio obtained reduced errors and were considerably robust. FLBs, OGBs, SBO2, and Beans Fusion achieved worse results. As an example of the system failures observed in the evaluation, wrong feature matches detected by OGBs are presented here. In this case, we can see an incorrect matching between landmarks projected onto the last keyframe and the features of the current image. This is related to a wrong initialization caused by the robot's movement from the very beginning of the sequence. In addition, REBO suffers from another tracking failure. We can see that in the case of sequence 3, when the robot stops for a moment, all the previously detected edges become red, indicating that REBO lost the scene depth. From this moment onward, the quality of its estimation decreased considerably. In the evaluation of ORB-SLAM3, we noticed a large difference in estimation errors made between initialization and the rest of the trajectory. When ignoring initialization errors, we observed the following results. Here we include the corresponding results for S-MSCKF to compare, discarding the same initial parts of its estimations. Another important aspect of the evaluation is the analysis about processing time. We measure the time between the arrival of an image and the first published post that was estimated, taking into account that information and all IMU messages that correspond. The initialization procedures were avoided, and we assured that no stereo frame was lost. The fastest system is SVO2, a sparse method that only extracts features for keyframes. Among the slowest systems we find VIO, S-MSCKF and Beans Fusion.